Welcome students. So let's continue with the chapter that is some p block elements, and in the last class I have explained you till the oxidation state of the group 13 elements. So now further in this chapter we are going to discuss about the chemical reactivity for the group 13 elements. Means all the chemical properties will be discussed out here for the group 13 elements. So first, for the group 13 elements, we know that the elements are boron, aluminium, gallium, indium, and thallium. So here the boron is having a diagonal relationship with that of the next group element, that is the silicon. Okay, carbon, silicon, germanium, then tin, and then lead. These are the group 14th element. Okay, so here we will see that there is a diagonal relationship between the boron and silicon. Many of the properties here is matching for the boron, which is similar to that of the silicon. The same property was being discussed out for the s block elements also, where the properties of the lithium, okay, it was similar to that of the magnesium, which was present diagonally to it. And similarly for beryllium, the diagonal relationship was between beryllium and the aluminium. Okay, so like this only the diagonal relationship is also present for the non-metal silicon and non-metal boron, while other elements, that is aluminium, gallium, indium, and thallium, they all behave as a metal. Okay, so here in the chemical reactivity we will see that the boron, it is forming a non-metallic compounds, and it is forming non-metallic compounds, and the crystalline form is very hard, inert, and non-conducting for the boron. For the boron, it is a crystalline structure only. It exists in crystalline form, and the crystalline structure of boron, it is inert in nature, and also it is a insulator. Okay, it is a insulator. Now let's move and discuss about the chemical reactivity for the other elements. So next to this, next to boron, aluminium is there. So aluminium is a reactive metal. Okay, it is one of the reactive metal, but it forms a protective covering. Okay, reactive. It is relatively reactive as comparison to other metals, but it forms a protective covering or protective layer of aluminium oxide, aluminium oxide, that is Al2O3, है ना? So due to the formation of this aluminium oxide layer over the metal, aluminium metal, what happens? It behaves as an inert. The reactivity of the aluminium will decrease out there. Okay, although it is attacked by alkali there. Okay, it is inert after the formation of this aluminium oxide. It behaves as inert to acids, but reacts with bases or alkalis readily. Okay, next, gallium, indium, and thallium, they are relatively soft. We have discussed this thing in the previous class also, that gallium, indium, and thallium, they are relatively soft as comparison to that of the boron, and as comparison to that of the aluminium. Okay, and hence reactive, and hence are reactive as they are soft. Okay, as they are soft, are soft, so are reactive. So are reactive and readily reacts with acids and readily reacts with acids. Okay. Also, we will see that the ionization potential for boron, okay, it is quite high. The ionization potential for boron is quite high, and due to this reason, it accepts electron, not it does not donate the electron, but it accepts electron, okay, and hence it show which kind of behavior? It shows a non-metallic behavior there. But the in special conditions, we can see that the boron can form tetravalent, oh sorry, trivalent cation, okay, in conditions where we can provide energy for the boron to remove the electrons there, so there it can form trivalent cation there, okay. But generally we will see that the boron in normal condition forms covalent bonds only. It does not forms the ionic bonds, okay. Next, unlike boron, other group 3, okay, other group 13 elements, other group 13 elements, okay. One more thing to know, that the name of the group 13 element is also group 3a elements, okay. In the older modern periodic table, you will see that the name here, it is been mentioned for this group as a group 3a, okay. So keep this thing in your mind also, that it can be called as group 3a also. So here the other elements of the group 13 elements, they form ionic compounds, okay. They form ionic compounds in aqueous solutions, in aqueous solution, okay. One example can be there, AlCl3, which is a Lewis acid, okay. So this is a very famous means a very useful catalyst it is, because in it is generally forming compounds such as AlH2O 6 3 plus, which is ionic in nature, okay. Except thallium, except thallium, all other group 13 elements have trivalency, means they are having plus 3 charge, while thallium is more stable. Thallium compounds are more stable in plus 1, okay. It is more stable in plus 1. For example, we can see the compound of borons as Bf3, BCl3, Bi3, okay. And in the case of boron, we will see that it is forming electron deficient compounds. BH3 is also there. Okay, boron. We will further study about boron. Okay, so electron deficient compounds are being formed out by the borons. And due to this reason, what will happen if I am taking an example for the borons compound, that is BCl3. Okay, so here BCl3, it will be behaving as a Lewis acid. Okay, BCl3, boron chloride, it will be behaving as a Lewis acid, while the ammonia here, I am using ammonia here for reaction between the boron chloride and ammonia. So what will happen here? The lone pair of electron, it will be donated to the boron. Okay, here it will be donated to the boron, as boron is having 3 valence electrons, which is been shared with chlorine here. Like this, you can see that the chlorine is sharing one electron with the boron, but still here boron is having only 6 electrons in its outermost shell. So here the nitrogen of the ammonia, it will donate a lone pair of electron to boron in order to complete the octet for the boron, and hence a compound that is a coordinate compound or a complex compound will be formed out here for the boron chloride. So this kind of nature will be seen out there. Okay, this kind of nature will be seen out there, and the Lewis acid character, the Lewis acid character can be represented, can be represented by using this particular relation, that is Bx3, that is the boron when it is compounded with halogens. Okay, when it is compounded with halogens, then it is having more basic Lewis acid character as comparison to that of the aluminium halides, while the gallium and the indium will be having the lowest. And thallium will not show any kind of Lewis acid character. Okay, because it is having plus one valency only. Okay, it is showing plus one valency only there. Next is the reactivity of the group 13 element towards the air. Now we are going to specifically see the reactions of each element of the group 13 elements with different compounds or different elements. Okay, so first we are going to see the reactivities of the group 13 elements with the air. So here the general formula for the group 13 elements with the air is that 4E, when it reacts with the oxygen present in the air, it will form oxide, that is 2E2O3 on heating. Okay, so here you can take example, that is if I am using 4 boron, so boron will get oxidized when reacting with air to form borate or borax. Okay, boron trioxide. It is named as boron trioxide. Similarly, aluminium gets oxidized. Aluminium's outermost layer gets oxidized with the oxygen present in air to form aluminate, aluminium oxide, aluminium trioxide. So here we will see that the nature of these oxides which are formed by the boron, aluminium, they are generally amphoteric. Okay, they are generally amphoteric. Okay, especially the aluminium. Aluminium's nature will be amphoteric here. Okay, while the boron trioxide is acidic and it reacts with the basic only. Okay, it is having a acidic nature because it is having more non-metallic character. It is more non-metallic. So hence it will be having which kind of nature? It will be having more acidic nature. While in the case of other elements, they will be having amphoteric. The oxides of the other group 13 elements will be having amphoteric nature, while the boron only will be having the acidic nature. Okay, so for nitrides, when the group 13 elements react with the nitrogen gas of the air, so they form 2E solid plus N2 gas, gives on heating it will give 2En. Okay, so here for example if I am taking boron, it will give 2Bn, boron nitride. Okay, so aluminium nitride is also formed. Okay, and as I have told you that aluminium and gallium oxides are the example for the amphoteric oxides. Okay, they are amphoteric oxides. They behave with acids as bases, and they behave with a bases as acids. Next, reactivity of group 13 elements towards the water. So here, boron does not react with water. Okay, pure boron does not react with water, while aluminium is also not attacked by cold water. Okay, boron does not, okay, to be more precise, pure boron does not reacts with water, while aluminium does not react with cold water, does not react with cold water. Okay, it does not react with cold water, while 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 we will see that amalgamated amalgamated aluminium aluminium reacts with cold water to form aluminium hydroxide. Okay, it will form aluminium hydroxide there, but it must be amalgamated. Okay, amalgamated. Pure aluminium will not react with cold water. Gallium and indium are also neither attacked by cold water nor by hot water. Okay, gallium and indium are non-reactive towards water. Towards water. Okay, but if large amount of oxygen is there, then gallium can form gallium oxide. Okay, on the surface of the gallium a little bit reaction can be observed out, but very large amount of oxygen must be there, means excess of oxygen must be present out there for the formation of gallium oxide. Okay, next is the reactivity of group 13 elements towards acids and bases. So boron does not reacts with acids or bases even at moderate temperatures. But aluminium, okay, it reacts with the acid and it generally dissolves in mineral acids. Okay, and it will be ionized there in the mineral acids to liberate hydrogen gas. Also, due to the amphoteric nature of the aluminium, you will see that it can react with the bases also. Okay, it can react with the bases also, and it will form their aluminium complex of aluminium hydroxide with sodium. Okay, and hydrogen gas will be liberated out there. However, concentrated nitric acid make aluminium passive by forming a protective layer of oxide there, and where it does not react with then further with the nitric acid there. Okay, so exception is there that aluminium will not react readily with the nitric acid. Okay, so there are some heating or some catalyzation will be required out there. Next, boron is generally inert at lower temperature, but when at higher temperature, it will react with a mixture of concentrated, with a mixture of dilute HNO3 and concentrated H2SO4. But temperature must be kept higher here in order to form boric acid. Okay, in order to form boric acid, which is one of the famous compound which is generally used out in the medication for the medication purpose also. You have heard about this boric acid. So boric acid is generally formed out by using the using this process, that boron is being heated with dilute HNO3 and in the presence of concentrated H2SO4, so it will form okay, and here the ratio must be 2:1 ratio. Okay, 2:1 ratio must be there in order to form the boric acid from boron. Boron can also react with fused caustic alkalis like NaOH or KOH. Okay, fused means they must be in their molten state. Okay, so in their molten state only the boron will react with them, but not in their aqueous or in the solvent state. They will react only in the fused state. Okay, so in the fused state and at higher temperatures such as greater than 773 Kelvin, you will see that the formation of sodium borate, sodium borate takes place with the liberation of hydrogen gas, with the liberation of the hydrogen gas. Boron also dissolves in, okay, boron will also dissolve in fused sodium carbonate. Okay, infused sodium carbonate, boron can be dissolved, in the mixture of fused sodium carbonate and sodium nitrate to form sodium borate, and sodium nitrate will be recovered back there with carbon dioxide gas. Okay, so this is the formation of sodium borate. Okay, these two processes are used for the formation of sodium borate, while this is the process used for preparation of the boric acid. Next, reactivity towards halogen. So generally, all the group 13 elements um, except the last one, that is the thallium, all other forms the tri halogen. Okay, trihalides. So here when the group 13 elements are reacted with halogen, so they will form the compound that is trihalide compounds, which are generally gaseous. Okay, and here E are the 13th group elements, and X can be either fluorine, chlorine, bromine, and iodine. Okay. Next is the some anomalous properties of boron. Anomalous properties for boron. So as we know that all the first elements of the group, they are having some of the different properties as comparison to that of their other members of the family. Okay, that is the group other members which are present in their group, as that. So like that only the boron is also having some different properties, some anomalous properties as comparison to the other elements which are present in the group 13. So the first property is that it is behaving as a non-metal. Okay, this one is the most anomalous property, that other group 13 elements are behaving as a metals while the boron is behaving as a non-metal. Okay, the first here we are going to see that boron forms hydrides while other elements of the group 13 elements does not form the hydrides. Okay, And if they are forming the hydride, then the general formula for the hydride is EH3. And the thermal stability of these hydrides, okay, the thermal stability, it will decrease as we move down in the group. The thermal stability of the hydrides formed by the group 13 elements, it will be decreasing on moving down in the group, on moving down in group. Okay, means boron hydride is more stable as comparison to the aluminium hydride, which is more stable as comparison to the gallium hydride, which is more stable as comparison to the indium hydride. Boron forms a number of hydrides. Okay, boron is having the nature that it will form very different kinds of hydride, and the general formula for the hydrides which are formed by boron, it is Bn Hn plus 4 and Bn Hn plus 6, where N is the number of borons attached to hydrogen. These compounds of boron with hydrogen, they are termed as boranes. Okay, they will be termed as boranes. So for borane, you can see if I am taking B2, so it will be H6. So it is diborane. The name of this compound will be diborane. Okay. Similarly, 4 are there, B4. So it will be H8, I think so, na? B4H10. This will be there. This will be the formula. Sorry, not 8. It will be B4H10. So there it will be tetraborane. Tetraborane. Okay. So like this, the name of the compounds are there for the boron, and many of the different types of hydrides will be observed out there for the boron here. Next, for aluminium forms polymeric hydrides. Polymeric hydrides. And the general formula for it, it is AlH3N. Okay, AlH3N. Now the hydrides of the boron, they are generally weak Lewis acids. Okay, hydrides of boron are weak Lewis acids. Weak Lewis acids, and they form adduct. Adduct means addition compounds. Okay, adduct with strong Lewis acids. With strong Lewis acids such as EH3 forming with B. And here we will see that the E can either be aluminium or it can be gallium. Okay. So therefore they form complex hydrides. Okay, they will form complex hydrides. For example, the example for the complex hydride can be lithium borohydride. Lithium borohydride. Okay, lithium gallium hydride, and one of the famous, very famous compound, that is lithium aluminium hydride. Okay, so lithium aluminium hydride, it is one of the famous element, which it is one of the famous compound which is used as a very good, very strong reducing agent. It is one of the strong reducing agent. Okay, and it is been used for the reduction reactions, for the carrying out of the reduction reaction. So how this lithium aluminium hydride is formed? The lithium aluminium hydride, it is formed when lithium hydride is reacted with aluminium chloride in the presence of ether. So there the formation of lithium aluminium hydride will take place with the formation of lithium chloride. It is a white crystalline solid and soluble in diethyl ether. It is very powerful reducing agent, है ना? We have discussed this thing before also, that it is one of the powerful, strongest reducing agent. The next anomalous property for the boron, it is formation of halides. Formation of halides. So group 13 elements, as we have discussed before, that group 13 elements form trihalides, है ना? Trihalides except TLI3. Okay, except TLI3. The halides of borons are covalent. Okay, they all are covalent and monomeric in nature, means they are singular compounds. No polymeric nature is there. Here we will see that the boron here, in the case of halides, the boron here, it is having sp2 hybridization. Okay, sp2 hybrid orbitals are being present, which adopts trigonal planar structure, which forms trigonal planar structure, planar structure to form the halides. Okay, to form the halides, it is having which kind of structure? It is having trigonal planar structure. Okay. Also, we will see that all the halides of boron are volatile. All the halides, what are the properties for the boron halides? They all are volatile. Volatile means very, very reactive. Highly reactive. Okay, highly reactive. And they are monomeric. Highly reactive, and they are monomeric. While we will see that two, that is BF3 and BCl3, are in gaseous state at room temperature. Okay, at room temperature they are at gaseous state. Whom? BF3 and BCl3. Also in the BBr3, we will see that BBr3, that is boron tribromide, is a volatile liquid, is a volatile liquid, very, very reactive liquid. It will readily will convert to gaseous state, while Bi3, it is a solid. Okay, Bi3 will be a solid. Here in the compounds of the borons trihalides, we will see that it is having electron deficiency there. Okay, electron deficiency will be there. For BF3, if I am taking the example here, we will see that the 2s orbital and 2p orbital of the boron, it is been having 1 electron there. Okay, and at excited state, what will happen after the hybridization? Okay, after the hybridization here, what will happen? sp2 hybridization, we will see that the boron, okay, it will be having the structure as 1, 2 and 3 hybrid orbitals. Okay, and they are been forming sigma bonds with the p orbital of the 3 fluorines. Okay, so this will be the trigonal planar structure here. Okay, for the boron, and here we will see that the vacant orbitals are been relieved out, is been present here. Two vacant orbitals is been present for the boron here. Okay, here you can see that two vacant orbitals are being present here. So due to this reason, the boron act as Lewis acid. It will be acting as Lewis acid. Okay, so here the formation of dative bond or covalent bond or coordinate bond will be formed out there. Okay, for the boron with Lewis bases such as ammonia. Okay, and formation of dative bond or coordinate bond will take place here, which are also called as complex compounds. Okay, complex compounds. So here the strength for boron Lewis acids, boron Lewis acid is been determined by the relation that BBr3 it is more having the Lewis acid character as comparison to the BCl3, and BCl3 is having more acidic character as comparison to the BF3. Okay, so this is the relation. Okay, this is the relation for the reason for the Lewis acid character for the boron. Okay, as it is having less compound form, less number of electrons to complete its octet, so it accept electrons and it behaves as a Lewis acid there. Next, in the case of aluminium, we will see that aluminium will not combine with any other compound. Okay, it will not combine with any other compound. It will combine with other molecule of AlCl3 only to form a polymeric. Here the dative bond will be formed between the chlorine and the aluminium of the two aluminium chlorides here, and there they will form a polymeric structure like this, dimer. Okay, they will form dimer like this, and after this formation of this dimer they will be more stable as comparison to that of the boron here. But this dimer when it is reacted with water, okay, this dimer when it is reacted with water, so it will undergo a reversible reaction to form aluminium hydrated complex. Okay, a complex will be formed out, a complex salt will be formed out, aluminium hydrated complex salt. Okay, this dimer is generally famous for this reaction only. Okay, next, some of more reactions are being left out for the means some of the characteristics for the boron is been left. So we will discuss that characteristics in the next class, and also we will start the next group, that is the group 14 elements in the next class. So for today's class, I am ending the class here only. We will meet up in the next class. Thank you.